Once the production of elements and modules, or in short, building components, has been completed in the factory and they have reached the construction site, the part of the project begins where they are used to build various types of buildings: private houses, apartment buildings, offices, schools, kindergartens, and various other residential or public buildings. At the end of the factory work, all the volumetric elements are packed in strong film to protect them from the weather both during storage and during transport. However, the transport route can sometimes be long and also include several lifts, which is why the protective film can also be seriously damaged. Therefore, when the modules have arrived at the construction site, during unpacking, the site manager checks the packaging of the modules to identify possible damages. When the building erection or assembly begins, the packaging film must be partially removed, after which the modules also become susceptible to precipitation. Therefore, the site team must take into account both the current weather and the long-term weather forecast in order to plan all assembly work rationally and without disruptions. Compared to planar element houses, the erection of modular houses is significantly more moisture-proof, as the assembly time is significantly shorter, and the risk of moisture damage is lower. Modular houses can be erected in both light snowfall and light rain, keeping critical areas protected from precipitation. But, in the event of heavier precipitation, the erection of the building must still be interrupted. During the winter, when working on sites, then must take into account the short daylight hours, low temperatures, slippery conditions, snowfall, strong winds, and other weather-related circumstances that make outdoor work difficult. The short daylight hours and low temperatures mean that a large part of the work must be carried out under floodlights and in thicker clothing to protect against the cold, which is why the entire work process takes longer and requires greater attention to ensure that the work is carried out in a high-quality and safe manner. Before the start of construction work, if there has been heavy snowfall and the area under the house inside the foundation is buried in snow, it must be cleared of snow to prevent a large amount of moisture from accumulating under the house. The area under the house may not be able to drain moisture if a radon barrier or insulation boards have been used, which is why moisture can remain there for a longer period of time and cause mold to form on the surfaces. In the case of multi-story buildings, if a layer of snow has fallen on the lower modules, it is removed using blowers so that the base surface is free of snow before the next module is lifted on top of it. During the summer, the main factors hindering erection work are rain and strong wind. Above a certain wind speed, crane lifting is not permitted, and the entire erection process must be stopped. In the event of heavy rain, work will also be stopped if it is not possible to keep the surface of the modules being assembled dry or to dry it quickly enough. The impact and amount of precipitation must be assessed separately each time. This is usually done by the project manager. If the upper floor module is lifted onto the lower one, in the event of rain, it must be possible to dry the upper surface of the lower module before the new module is lifted on top. If this is not possible, the construction of the building must be stopped. Precipitation and moisture are usually removed using blowers. The erection of a building, meaning the lifting of the volumetric elements from the car or temporary storage area to the foundation and, in the case of multi-story buildings, also on top of each other, takes place at a fast pace. In most cases, when one module has been lifted from the car to intended location and the car has left, the next car drives to the crane lifting area and preparations begin for lifting the next module. The covering films are removed from the walls connecting the adjacent modules, and the lifting slings are attached. The entire building erection process must take place according to a previously prepared plan. There is a specific order in which the modules are lifted, and each module also has its own location in the building. Therefore, it is important to strictly follow the logistics of the vehicles that transport the modules to the construction site and the prepared erection plan. Two main lifting methods are used when lifting modules. Lifting eyes are installed in the corners of the module, and the module hangs from the slings when lifted. Or, slings are placed underneath the module so that the module rests on the slings. The most common option is where the lifting slings pass under the module. In this case, the structural solution of the module is easier to implement from a lifting point of view. Additional reinforcements must be installed in the designated places in the floor panel that support the slings so that the module does not break or deform excessively at the lifting point. Before installing lifting slings, it is important to make sure that the slings are undamaged. Broken or defective lifting slings are not permitted and must be replaced with proper ones. It is important to remember that slinging work may only be carried out by employees who have successfully completed the relevant prior training. The module, which is lifted by a crane onto the unfinished building, is guided to its intended location using guide straps attached to the module. Usually 2 guide straps are enough, but there can be more if necessary. The lifted module is adjusted precisely into place, and the levelness is also checked. During the lifting work, preparatory work can also be done to receive the next module. During this process, temporary moisture protections are removed, and sealing wool strips are installed at the base of the module. Once the module is in place, the ends of the lifting slings on the free side of the module are untied so that the crane can remove the slings and start lifting the next module. The joints of the installed modules must be connected to each other to form an interoperable whole. The connected modules ensure that the building can withstand both wind and, if necessary, earthquake loads. External joints between modules can be in both horizontal and vertical planes. During the erection of the building, the joints are made in the horizontal plane. At the same time as the joints are made, the joints are also made weatherproof so that precipitation does not enter the space between the modules. If necessary, temporary covering solutions are also used to make permanent joints later. It is important that the tools and materials intended for making joints are assembled in advance and available at the construction site. Horizontal joints between volumetric elements are sealed with mineral wool. In most cases, manufacturers have the sealing wool strips partially attached to the wall element at the factory to reduce site work. When one module is lifted next to another, the sealing wool strip attached to the wall is pressed together. This creates a tight connection between the elements. If necessary, additional insulation can be added during the erection work. As a result of the sealing, the airspace between the modules must remain closed. This is necessary both to limit possible convective, that is caused by temperature differences, air movement, and to prevent the spread of fire in the event of a fire. After the joint has been sealed with mineral wool, it is covered with a strong stiffening board, which is nailed or screwed to the edge board of both adjacent modules. The stiffening board, which can be OSB for example, binds the modules together. Figuratively speaking, it is like making a seam. On top of the module, the joints in the ceiling or roof plane are sealed as soon as possible, immediately after the modules have been lifted into place. Acting quickly is extremely important here, as in the event of rain, rainwater can penetrate between the modules and cause serious moisture damage there. The joints on the external walls of the modules must be sealed with mineral wool before final closure, as is the case with roofs. Sealing prevents penetrating air between the modules and helps to cut through possible thermal bridges. After sealing, the module walls are connected with a strong wood-based board, which can be covered with an additional insulation layer and wind barrier if necessary. Each manufacturer has its own standard detail solutions for connecting the modules together. Before the joints are closed, the moisture content of the structural timber is measured. If the moisture level exceeds the maximum permitted value, which is generally 18%, the joint must not be closed, and it must be waited for the moisture level to drop, meaning to let the timber to dry. If the timber is so wet that natural drying would take too long, mechanical drying must be carried out using moisture dryer. After the work on sealing the joints is completed, a mousetrap and insect screen are installed in the base of the building. On taller buildings, a fire-resistant profiled sheet or heat-expanding gasket is also attached between the battens. The areas around ventilation pipes and other openings in the exterior walls are sealed to make them airtight. Then, the outer lining is installed on the rafters. All joints between the modules remain hidden by the lining. If the building is intended to have balconies or walkways, strong metal supports are attached to the part of the module walls that join them. The supports can withstand the structural load from the additional element, live loads, and possible snow loads. Most often, balconies or walkways are supported on one side by supports, and on the other side by posts or hangers anchored to the walls. For balconies, a so-called cantilever solution is also used. In this case, the floor of the living space and the balcony are on the same beams and separate supports are not needed. With this solution, time-consuming work on lifting and installing balconies on the construction site is eliminated. If the railings are also installed in the factory, the amount of site work during the installation of the balconies is minimized. The joints between walls, balconies, and walkways must be made in such a way that rainwater that gets into them cannot enter the structure. In most cases, the panels of balconies and walkways are already covered in the factory with a strong and waterproof covering material, which is similar to the covering of flat roofs. The balcony flooring is screwed up to the wall of the room element and fixed watertight. Different manufacturers may have quite different standard solutions, depending on the materials used. Both balconies and walkways must have a slope away from the house, or if a drain is installed for internal drainage, the slopes must go towards the drain. A terrace board resting on a deep impregnated substructure is usually installed on top of the covering material for balconies and walkways, but there can be several other solutions here too. After the balcony elements are installed, work begins on the walls and ceilings. First, the joints between the elements in the ceilings can be sealed. If fire resistance requirements are specified for the elements, it must be ensured that the balcony or walkway elements provide load-bearing capacity and tightness for the prescribed time in a fire situation. Therefore, the use of both fire insulation and fireboards may be required. To prove the quality of work, a mark is placed in the appropriate location, and the work area is photographed to include a photo with the proof document. Walls adjacent to balconies or walkways are covered with siding. Flat roofs usually use an internal drainage system. Gutters are made on the roofs to drain rainwater, which have a slope towards the drainage funnel. Through the funnels, rainwater flows into the drainage pipes, which are located in the building's shafts, and go under the building. The water then flows away from the building into the rainwater well. Roofs can also have larger openings, such as skylights, roof access hatches, smoke extraction hatches. Depending on the need, the hatches can also be translucent. Smoke extraction hatches are used to remove smoke, heat, and toxic gases from a burning building in the event of a fire. Their purpose is to create a smoke-free zone above the floor, and thus ensure safer evacuation and the work of the rescue team. Roofing work also includes the installation of ventilation chimneys for the building's internal ventilation system. It also includes the installation of safety loops with flags, where safety belts can be attached if necessary, and the sealing of penetrations. Elevations called parapets are installed on the edge areas of the roof. The roof side of the parapet is covered either partially or completely with roofing material. The top surface of the parapet is covered with metal sheeting, which must be sufficiently inclined towards the roof so that there is no standing water on it, and so that dirt accumulated on the parapet moves towards the roof under the influence of rainwater and does not stain the facade. Module joints that remain inside the building occur when a space consists of two or more adjacent modules. In this case, openings of the same size are left in the adjacent walls of the modules so that a larger common space can be formed. Internal joints, both horizontal and vertical, must be made in a way that ensures airtightness between the elements and, if fire resistance requirements are met, the necessary fire resistance. Before sealing the joint between modules, the moisture content of the structural wood is checked. In case of excessive moisture, sealing work is not started until the excess moisture has dried out. In the module joint, the gap between the modules at first need to seal with fire-resistant insulation material. Fire insulation protects the joint elements from direct fire from the side and prevents the spread of fire into the space between the modules. Load-bearing structural elements must maintain their load-bearing capacity for a specified period of time in a fire situation. Therefore, it is extremely important to prevent entering fire into space between the modules. After the insulation is installed, the modules are connected to each other with a strong wood-based board. Such rigid connections provide the required mechanical strength to the joints, binding the modules into a single whole. Finally, the required number of gypsum boards are added to the wood-based panel. Gypsum boards, in turn, add fire resistance to the joint and serve as a base for finishing materials. In this case, it is important to pay attention to the type of gypsum board and follow the project exactly. Both the thickness of the boards and their fire resistance properties are important. If the joints are in the external walls or in the ceiling of the last floor, then in addition to the mineral wool, an airtight joint must also be made to the vapor barrier. Generally, strips of vapor barrier film are left protruding at the joints, which overlap each other. The vapor barrier joint is taped. Then the boards are installed and the room side layer of boards is finished. A large part of the communications is already installed in the modules during factory production. On the construction site, these details that could not be installed during production are added, connections between the communications are made, and control tests are performed. All communications that are not autonomous, such as cables, domestic water, and heating, must be connected to external networks that enter the building through shafts. For this purpose, pipe and cable outlets are brought out from under the house, from the ground, and are located in places where the shafts planned for the building are located. In the case of larger buildings where a garage is located beneath the structure, communications must be secured to the ceiling of the garage, and penetrations should be made in areas where shafts are located. It is also important to pay attention to the seals of the penetrations. The seals must be made in such a way that neither fire nor toxic gases can enter the spaces above the garage in the event of an incident. Most garages are also equipped with an automatic fire extinguishing system, commonly known as a sprinkler system. It is possible to install communications in shafts to a greater or lesser extent already at the factory. In this case, the time for site work is somewhat shorter, and connections are made through a hatch in the shaft wall. However, many manufacturers prefer to leave the shaft wall open and install communications on the construction site. This way, it is more convenient to make connections, especially if there are many different communications and there is little space in the shaft. The water pipes in the shaft are connected to the water closet manifolds, from where the pipes continue to the water appliances in the living room, various faucets, and cisterns. To detect possible water leaks in the pipes, a pressure test is performed before connecting to the water system. The pipe is leak-free if the pressure gauge does not indicate a pressure surge within the specified time. The sewer pipes are connected to the drains of sinks and drains. They join a central pipe in a shaft, which exits through the shaft under the building, where the necessary connections are made to the central sewer system. The heating pipes inside the dwelling are connected to the manifolds of the heating cabinet. In the case of a central heating system, they are connected to the building's heating unit via pipes located in shafts. The sprinkler pipes are connected via a shaft to the sprinkler center, where the entire sprinkler network control and monitoring system is located. Before final pressurization, pressure tests are performed on the distribution systems to detect possible leaks. After the building is erected, a power cable is brought to the electrical panel of the living room, which starts from the main panel of the house. The main panel of the house is in turn connected to the main cable, which is located under the house. The necessary wires are pulled into the conduits installed in the factories for electrical wiring at the construction site. The wiring is connected to the electrical panel in the living room and to the outlets for electrical consumers. Low-voltage cables are also often installed, which are necessary for security systems, audio and video systems, computer-related systems, and the like. Ventilation systems used in buildings can be either local or central. In the case of a local ventilation system, each living space has its own ventilation unit, which can also be integrated into kitchen furniture. In this case, the owner of the living space is responsible for the maintenance and repair of the unit. In the case of a central ventilation system, one ventilation unit serves many living spaces. In the case of local systems, ventilation pipes, sound absorbers, and ventilation units are already installed in the modules at the factory. If the living space consists of several modules, then the only work that needs to be done on site is to connect the pipelines of neighboring modules and balance the system. Central systems are used, for example, in hotels, school buildings, dormitories, and other buildings with long corridors, behind which a pipe can be installed, from which the extracts go to different rooms. For the ventilation unit, which is transported to the site separately, as it is usually large and heavy, a separate chamber can also be built, which can be located on the roof of the building, in the attic, or in the basement. If a central ventilation system is planned for a building, a greater amount of site work must also be taken into account. In the case of central ventilation, there is significantly more piping installation and connection work than in the case of a local system. Despite the precautions, the modules may suffer some damage during transport and lifting operations, which becomes apparent when they are removed from the packaging film at the construction site. One of the most common problems on the outside of the module is the crushing of factory-installed metal window sill, as well as various damages to the outer lining. Generally, all necessary replacement and repair work is carried out after the building is erected. Interior renovation work also involves the transportation and lifting of modules. During lifting, especially when lifting long modules, the modules may bend, and if the stiffening of the areas susceptible to bending is insufficient, cracks may appear in the interior finish. Such damage most often occurs in the corners of openings where the wall section covered with a panel is smaller, but also in the corners of adjacent walls. Cracks can also occur in the corners between the ceiling and the wall. These damages can usually be repaired with flexible acrylic and paint. If the paint repairs remain noticeable, the entire ceiling or wall will need to be repainted. If cracks appear in the middle of the wall, the damaged part of the wall must be opened. A new layer of boards with a covering fabric must be installed and finished. In such cases, the necessary paints, putties, and tiles will be brought to the site. Tiled walls in wet areas are also vulnerable to damage. Tiles in these areas can crack or come loose. Frequently, areas most likely to be damaged are left ungrouted or untiled during manufacturing, and the required work is scheduled to be finished on site. Particular care must be taken with large-sized tile coverings. Repair and finishing of cracked areas is carried out towards the end of the interior work, along with other finishing works, such as finishing of module joints and communication boxes. After the exterior work is completed, the scaffolding around the building is removed, and the area around the building is tidied up. Asphalt or stone paving is installed if necessary, and grass is sown and plants are planted. Upon completion of the interior work, the premises will be cleaned. A major cleaning will be performed, and the building will be prepared for handover to the client. If the client is a developer, a model apartment is usually also furnished.